Right now, all around you, stretching far beyond the sky you can see, there is a cold so extreme it barely even counts as temperature. The space between the stars sits just a few degrees above absolute zero, the lowest temperature anything in the universe can ever reach. Scientists measure it at 2.7 Kelvin, a faint static of the Big Bang still echoing through space after 13.8 billion years. But here's where it becomes unsettling. Space isn't cold the way you understand cold. There's no air to freeze, no wind to bite your skin, no sensation at all. Because temperature, as we experience it, depends on something being there. And in space, there almost isn't. No particles to carry heat, no medium to hold warmth. Just an overwhelming emptiness where energy has nowhere to exist, nowhere to stay.
And what you're really looking at isn't cold. It's the absence of everything that makes warmth possible. And it doesn't exist in some distant corner of the universe. It dominates it. Over 99% of everything that exists is this near-perfect void, silent, invisible, and completely indifferent to anything that enters it. Tonight, we're going to break that illusion apart, what temperature actually means in space, why you wouldn't freeze the way you think, and how the cold of the universe is far stranger and far more dangerous than anything on Earth. If this kind of perspective changes how you see reality, consider liking and subscribing. Now get comfortable, because once you understand what cold really means out there, it stops feeling familiar and starts feeling empty. The cold of space is not the cold of a winter night scaled up. It is not the cold of Antarctica, or the cold of the deep ocean, or even the cold of liquid nitrogen. It is something categorically different, something that does not operate by any of the rules your body knows. In space, the usual machinery of cold is missing. The medium that steals your heat is absent, and what remains in its place is a condition so extreme, so alien to everything living things experience, that the word cold barely begins to contain it. But here is the thing that makes this more than just a number at the bottom of a thermometer. The cold of space is not merely a physical property of empty regions between stars. It is a fossil. It is direct evidence of an event that happened 13.8 billion years ago. Every photon of that cold, every measurement of 2.7 Kelvin that scientists record from the most remote reaches of the observable universe, is a signal that has been traveling since before the Earth existed, since before the sun ignited, since before any star of the current generation of stars had yet formed. The cold is a message, and once you understand what it is saying, the universe becomes a fundamentally different place to inhabit. Prepare yourselves. We begin. The thermometer was invented in 1593. Galileo Galilei built the first crude version, a glass tube with a sealed end, using the expansion of air to measure temperature changes. Over the following century, the idea was refined, calibrated, and standardized, until by the mid-1700s the Fahrenheit and Celsius scales had given science a common language for hot and cold. These scales were built entirely around the behavior of matter on Earth. Water freezes at 32 degrees Fahrenheit at 0 Celsius. Water boils at 212 Fahrenheit at 100 Celsius. The numbers were chosen to bracket the experience of a species living on a wet, temperate planet surrounded by an atmosphere. They were never designed for the universe. The universe did not care. When astronomers began turning instruments toward deep space, they found temperatures that made Earth's coldest winters look like a furnace by comparison. But more unsettling than the numbers was the nature of what those numbers were measuring. Temperature, it turns out, is not a property of space itself. It is a property of matter. And in most of space, there is almost no matter at all. To understand why this matters, and you have to understand what temperature actually is. At the level of individual atoms and molecules, temperature is motion. A hot object is an object whose constituent particles are vibrating rapidly, colliding frequently, exchanging kinetic energy at a furious rate. A cold object is one where the particles have slowed. Absolute zero, the theoretical floor of all temperature, 0 Kelvin, minus 273.15 Celsius, is the point at which all molecular motion ceases entirely.
It has never been achieved in a laboratory. Quantum mechanics forbids it. But it defines the scale everything else is measured against. When you feel cold, what you are experiencing is the transfer of thermal energy from your body to the air around you. The air molecules near your skin collide with the molecules in your skin, and with each collision, as some of the kinetic energy moves from the faster-moving molecules in your warm body to the slower-moving molecules in the cooler air, your skin becomes the donor, the air becomes the recipient. The colder the air, the greater the difference in molecular speed, and the faster your body loses heat. This is conduction. This is what cold feels like to every living thing that has ever existed on this planet. Now remove the air. Remove all of it. Remove every molecule, every atom, every particle capable of colliding with anything else. What is the temperature of nothing? The question sounds philosophical, but it has a precise physical answer, and finding that answer required the full power of 20th century physics. In a perfect vacuum, in a region of space containing absolutely no matter whatsoever, and temperature as normally defined becomes meaningless. You cannot measure the temperature of nothing the way you measure the temperature of air. Nothing has no molecular motion to measure. Nothing collides with nothing. A thermometer placed in a perfect vacuum would eventually settle at some temperature. But that temperature would be determined not by the surrounding space itself, but by the radiation passing through it. Radiation is the only form of heat transfer that requires no medium. And radiation, it turns out, fills the entire universe. This is where the story becomes strange. You can survive in space without any problem that cold causes. If you were placed in a perfect vacuum, protected from radiation in all directions, your body would not freeze the way it freezes in cold air. Your body would actually overheat. And then in the absence of any medium to carry heat away from you, your own metabolic processes would quickly raise your core temperature to dangerous levels. Sweating would not help, because sweat requires air molecules to evaporate into. In a true vacuum, cooling yourself becomes the challenge, not warming yourself. Astronauts on spacewalks generate so much body heat that the greatest thermal engineering challenge is keeping them cool, not keeping them warm. This is not what movies show. It is not what intuition suggests. And it is the first of many places where the terrifying truth about space and cold parts company entirely from what human beings imagine. But we are getting ahead of the story. The temperature of space, the real temperature that defines what the cosmos is by default, cannot be understood without first understanding how heat moves in the absence of matter. And to understand that, you have to go back to the three mechanisms of heat transfer and recognize that two of them simply stop working the moment matter disappears. Conduction requires direct contact between matter. When you hold a metal spoon in hot soup, heat travels from the soup molecules through the metal's crystal lattice into your hand. Every step requires matter touching matter. In a vacuum, conduction produces a rate of heat transfer of exactly 0. Not close to 0. Exactly 0. Convection requires a fluid, liquid, or gas moving in bulk to carry heat from one place to another. The warm air rising above a heater and the cool air sinking to replace it. The churning of a pot of boiling water. The great oceanic currents that moderate Earth's climate, all of these are convection. In space, there is no fluid. Convection rate, exactly 0. Radiation is different. Radiation requires nothing. Every object above absolute 0 emits electromagnetic radiation. A warm rock sitting in a field radiates. Your skin radiates. The stars radiate. A spaceship in orbit radiates. The energy moves outward as photons, particles of light, and travels at 186,000 miles per second through vacuum that contains no matter whatsoever. When a photon is absorbed by another object, that object gains energy. This is the only mechanism available in space. This is the entire thermal universe of anything that exists beyond the shelter of an atmosphere. The implications of this are extraordinary, and they play out everywhere that human beings have sent machines and human beings into space.
On July 20th, 1969, Neil Armstrong and Buzz Aldrin landed on the surface of the moon. They spent 2 hours and 31 minutes walking on its surface. During that time, their spacesuits maintained a comfortable temperature around their bodies, in an environment that ranged from scorching to lethal, depending on which direction they faced. The engineering required to keep 2 human beings alive on the moon's surface was staggering. What made it so hard was not any single extreme temperature. It was the coexistence of 2 extremes separated by a distance of a few inches. Stand in the sunlight on the moon's equator during lunar noon. The surface beneath your feet has reached 127 degrees Celsius, hot enough to boil water. Turn around and put your back to the sun. The shadow side of a rock a few feet away is sitting at minus 173 degrees Celsius, cold enough to freeze carbon dioxide solid. These temperatures exist simultaneously, separated by a few inches of lunar rock, with no atmosphere in between to mix them, to moderate them, to smooth the gradient into anything survivable without engineering intervention. On Earth, the atmosphere is the moderator. Air absorbs solar radiation, redistributes it through convection, traps some of it via the greenhouse effect, and exports the excess by radiation from the upper atmosphere. The result is that Earth's surface temperatures, while ranging from minus 89 degrees Celsius in Antarctica to 56 degrees Celsius in the deserts of Libya, never approach the extremes that an airless body experiences under the same solar illumination. The difference between Earth and the Moon is not distance from the Sun. They are essentially at the same distance. The difference is air. Without air, every object in space is solving a private thermodynamic equation, balancing the incoming radiation it absorbs against the outgoing radiation it emits, with no other variable. The temperature an object settles at is determined entirely by this balance. A black object absorbs more and emits more. A shiny object reflects more and absorbs less. The orientation to the source of radiation changes everything. A surface facing the sun absorbs energy at a ferocious rate. A surface turned away from the sun absorbs almost nothing and radiates what it has into the void at whatever rate its own properties permit. And this is why spacecraft thermal management is one of the most complex engineering disciplines in the field. Every spacecraft currently in operation carries systems designed specifically to manage this balance. The James Webb Space Telescope, operating at 1 million miles from Earth, uses a sun shield the size of a tennis court to keep its mirrors and instruments at minus 233 degrees Celsius, cold enough to detect the faint infrared radiation from the most distant galaxies, while the sun-facing side of the sun shield reaches 85 degrees Celsius. Both temperatures exist on the same spacecraft simultaneously, separated by the layers of the shield. The difference is 318 degrees across a few meters of engineered material. The International Space Station experiences a temperature swing from minus 120 Celsius to plus 120 Celsius every 90 minutes as it cycles in and out of Earth's shadow 16 times per day. It carries an active thermal control system that includes ammonia coolant loops, heat exchangers, and enormous radiator panels that dump excess heat into space. Without that system, the station would cook in sunlight and freeze in shadow. The system must manage both extremes continuously, often simultaneously, because different parts of the station are in different illumination conditions at the same time. An unprotected human body in sunlight near Earth's orbit would reach fatal temperatures from radiation absorption within minutes. The same unprotected body in permanent shadow, far from any heat source, it would not freeze quickly in the dramatic way movies suggest, because the only heat loss mechanism is radiation, which is gradual. The body would radiate its heat outward, slowly, and the question of how long survival remained possible would depend on a careful calculation of the body's thermal mass against the rate of radiative loss. Neither condition is survivable, but they would kill you in completely different ways, at completely different rates, through completely different mechanisms. The vacuum does not kill you the way cold air kills you. It kills you by making temperature management entirely a matter of radiation physics, and your body was not designed for radiation physics. Now move further out. Move far enough from the sun and from every star that the radiation arriving from any single source becomes negligible. Move into the deep void between galaxies. The thermodynamics simplify dramatically.
without a nearby star to absorb. The equation on the right side nearly vanishes. The emission side of the equation continues, and the object cools. It cools and cools and cools until it reaches equilibrium with the radiation field that permeates the entire observable universe. That equilibrium temperature is not zero. It is not quite zero. It is 2.7 Kelvin. And it has a name, and an origin, and a story that reaches back to the first moment the universe existed. In 1964, two engineers at Bell Laboratories in Holmdel, New Jersey, were trying to build the most sensitive microwave antenna receiver in the world. Arno Penzias and Robert Wilson were not looking for evidence of the Big Bang. They were not searching for the origin of the universe. They were calibrating an antenna that had been built for satellite communication, trying to reduce background noise in the receiver to the absolute minimum possible. They were doing the unglamorous, meticulous work of engineering optimization. And they could not get rid of a persistent, irritating hiss. The noise appeared at every frequency they tried. It appeared regardless of which direction they pointed the antenna. It appeared during the day and at night. It appeared in summer and in winter. They checked the equipment. They replaced components. They found a pair of pigeons nesting in the antenna horn and cleaned out, in Penzias's words, a white dielectric material, which is a polite way of saying pigeon droppings. They cleaned every surface. The noise persisted. It was uniform. It was everywhere. It was equivalent to a temperature of approximately 3.5 Kelvin, which at the time they could not explain. Meanwhile, roughly 60 kilometers away at Princeton University, a team led by Robert Dicke was actively searching for exactly what Penzias and Wilson had accidentally found. Dicke and his colleagues James Peebles, Peter Roll, and David Wilkinson had been working from theoretical predictions that the early universe, if it had begun in an extremely hot, dense state, should have left behind a detectable residue of radiation. As the universe expanded and cooled, the original light of the fireball should have been stretched to longer and longer wavelengths by the expansion of space itself. By now, tens of billions of years later, it should appear as microwave radiation, uniformly filling the entire observable universe, and coming from every direction with equal intensity, equivalent to a temperature of a few Kelvin. They were building an instrument to find it when they received a phone call. The phone call was from Penzias. He had heard of Dicke's work through a mutual colleague and called to describe the noise he could not explain. Dicke listened, put down the phone, turned to his colleagues, and said, "Boys, we've been scooped. What Penzias and Wilson had found, by accident, while trying to eliminate it, was the oldest light in the observable universe. The cosmic microwave background, the thermal fossil of the Big Bang itself. Penzias and Wilson received the Nobel Prize in Physics in 1978. The discovery did not just confirm that the universe had a beginning. It established an absolute floor for the temperature of empty space. The radiation they detected, the radiation that fills the universe from horizon to horizon, corresponds to a temperature of 2.725 Kelvin, now measured to 4 decimal places with instruments of extraordinary precision. No object in the observable universe, no matter how far it travels from every star, no matter how deeply it retreats into the most desolate void between galaxies, can cool below this temperature, because the radiation is everywhere. It comes from every direction simultaneously. It is inescapable. 2.725. Kelvin is not merely a temperature. It is the temperature of the universe itself, measured at the present moment at this point in cosmic history. It is what the cosmos has cooled to after 13.8 billion years of expansion. And to understand why it is this number and not some other number, you have to go back to the moment the radiation was created. The universe began in a state of incomprehensible heat. The word "began" is doing more work in that sentence than it can comfortably carry, because the concepts of time and space, as we understand them, break down at the boundary of the Big Bang, but the physics is clear on what happened in the moments immediately after. The universe was hot beyond any temperature that currently exists anywhere in the observable cosmos, hot beyond what any instrument could measure, hot in a regime where the distinction between matter and energy was blurred almost beyond recognition. Every particle that would ever exist was there, but in a form so energetic that the particles we recognize today had not yet condensed out of the plasma. In the first fraction of a second, as the universe expanded and cooled with violent speed, The timescales involved insult the human intuition for duration. Within the first 10 to the negative 43rd seconds, the universe went through a phase of extraordinary rapid expansion called inflation, stretching from a region smaller than a proton to macroscopic scales in an interval so brief that there is no word for it in any human language that is not derived from mathematics. The temperature during this period exceeded 10 to the 32nd Kelvin. Numbers at this scale stop having intuitive meaning. The point is that the temperature was incomparably, categorically, incomprehensibly higher than anything that exists now. After inflation, the universe continued to expand, but at a more measured pace. As it expanded, it cooled. As it cooled, and the particles that make up everything we see began to condense from the plasma. Quarks combined into protons and neutrons within the first second. Protons and neutrons began fusing into the lightest atomic nuclei, hydrogen, helium, and traces of lithium, during the first 3 minutes. The universe at this point was still an opaque plasma of charged particles and photons, the fundamental particles of light, colliding with each other so frequently that light could not travel more than a tiny distance before being scattered. It was hot, dense, and opaque. This continued for approximately 380,000 years. Then something happened that permanently changed the nature of the universe. As the universe continued to expand and cool, the temperature dropped to approximately 3,000 Kelvin. At this temperature, for the first time, electrons could be captured by protons and held there. The hydrogen atom, consisting of a single proton orbited by a single electron, became stable. This transition happened rapidly on a cosmic timescale. What had been a plasma of free electrons and free protons suddenly became a gas of neutral hydrogen atoms. And when the electrons were captured, the photons that had been continuously scattering off them suddenly found themselves with nothing to scatter off. The universe became transparent. For the first time since its beginning, light could travel freely through space. The photons that had been trapped in the plasma were released all at once, in every direction simultaneously, from every point in the universe. This moment is called recombination. Technically a misnomer because the electrons were combining with protons for the first time rather than recombining, but the name has stuck. It is also called the surface of last scattering because it marks the last time those photons interacted with matter. After recombination, they traveled freely, and they have been traveling ever since. At the moment of their release, those photons corresponded to a temperature of about 3,000 Kelvin. They were visible light, somewhat orange-red in color. If you could have stood in the universe 380,000 years after the Big Bang, and if you could have somehow survived the conditions, you would have seen a universe that was not dark. Every direction you looked would have been as bright as the surface of a star. The universe at recombination was entirely filled with light, with no darkness anywhere, and because the light itself was the entire background. In the 13.8 billion years since that moment, the universe has expanded by a factor of approximately 1,100. Every wavelength of that original light has been stretched by the same factor. What was once orange-red visible light, with a wavelength of around 1,000 nanometers, has been stretched to microwave radiation with wavelengths of around 1.9 millimeters. The temperature of the radiation has cooled correspondingly, from 3,000 Kelvin to 2.725 Kelvin today. The light is still there. Every photon that was released at recombination is still traveling, filling the universe, arriving at every point from every direction. There are approximately 410 of these photons in every cubic centimeter of space, everywhere in the observable universe, including the space inside this room, yes, including the space between your cells right now. You are bathed in the oldest light in the universe, and it is too cold for your skin to feel. This is what 2.725 Kelvin means. It is not an arbitrary number chosen for some technical reason. It is the current temperature of a fire that lit 13.8 billion years ago, cooled by the expansion of space itself, still burning at a temperature so low that no instrument less sensitive than a precision microwave detector can register it at all. It is the baseline, the floor, the default temperature of the observable universe, set by a process that happened before the Milky Way existed, before the Sun existed, before the Earth existed, before anything that currently exists had yet formed. The cold of space is this old. 2.725 Kelvin is 2.725 degrees above absolute zero.
Absolute zero is minus 273.15 degrees Celsius. By any scale you choose, it is the coldest anything can possibly be. And the average temperature of the universe sits 2.725 degrees above it. To give this number its proper shape, consider what exists at various points on the temperature scale between absolute zero and 2.725 Kelvin. At 1 Kelvin, helium-3, the rare isotope of helium, is a superfluid. It flows without friction through any container you try to put it in. It climbs the walls of its container and drains itself. It behaves in ways that seem to violate the intuitions of classical physics, because at this temperature, quantum mechanical effects dominate the behavior of matter entirely. The world at 1 Kelvin is a world where the wave nature of particles is not a theoretical abstraction but the dominant physical reality of everything that happens. At 0.1 Kelvin, the exotic quantum state of matter called a Bose-Einstein condensate becomes possible for certain elements. A Bose-Einstein condensate is a state in which a collection of atoms all collapse into the same quantum ground state, behaving as a single quantum object, rather than a collection of individuals. It was predicted by Einstein in 1924, confirmed experimentally in 1995, and has never existed anywhere in the natural universe except in laboratories on Earth, cooled to temperatures far colder than anything in space. The coldest temperatures ever achieved in a laboratory are around 38 picokelvin, trillionths of a degree above absolute zero, achieved by cooling atoms in laser traps with extraordinary precision. These temperatures exist nowhere in nature. The universe, at 2.725 Kelvin, is hundreds of millions of times warmer than these laboratory extremes, and yet 2.725 Kelvin is extraordinarily cold by any ordinary standard. Water becomes solid at 273 Kelvin. The coldest temperature ever recorded on Earth's surface was 184 Kelvin at Vostok Station in Antarctica, minus 89 Celsius. Liquid nitrogen, used in laboratories and for flash freezing food, is 77 Kelvin. Liquid helium, used to cool the superconducting magnets in MRI scanners, is 4.2 Kelvin. The cosmic microwave background, the temperature of the universe itself, is 2.725 Kelvin. The universe is colder than liquid helium. The universe is colder than anything used in routine industrial or medical processes on Earth. The universe is colder than anything your body, your food, your climate, or your technology regularly encounters. Now scale up. Consider what 2.725 Kelvin means not just as a temperature at a single point, but as the average temperature of an object 93 billion light-years across. The observable universe, the portion of space from which light has had time to reach us since the Big Bang, spans approximately 93 billion light-years in diameter. It contains approximately 2 trillion galaxies. Most of its volume is not filled with galaxies, or with stars, or with any form of matter that radiates significant heat. Most of its volume is the vast, cold, nearly empty intergalactic medium, where the temperature sits at or near 2.725 Kelvin. The warm regions, the stars, the galactic centers, the accretion disks of black holes, are extraordinary concentrated exceptions to an overwhelming rule. They are islands of violent, intense heat in an ocean of cold that extends in every direction without limit. Every single one of those warm regions is, by the standards of the universe, a temporary anomaly. Stars burn for millions or billions of years, then go cold. Black holes accumulate mass and radiate for aeons, then evaporate into nothing. The cold does not end. The cold goes on. The cold is what remains when everything else is finished. This is the terrifying truth that the number 2.725 Kelvin contains. Not just that space is cold, but that cold is normal. Cold is default. Cold is what the universe is, and what it will increasingly become as time goes on. and the last stars burn out, and the cosmos settles toward its final state of equilibrium.
That the warmth you feel right now, sitting wherever you are, is an anomaly of the most extraordinary kind. Understanding why requires looking at the entire sweep of cosmic history, from the first moments to the last, and recognizing that the trajectory is in one direction. The universe is cooling. It has always been cooling. It will always cool. The rate of cooling is slowing as the difference between the universe's actual temperature and absolute zero narrows, but the direction has never changed and will never change. 13.8 billion years ago, the temperature was unimaginably high. Today, it is 2.725 Kelvin. In a trillion years, it will be lower. In 100 trillion years, when the last stars have burned out, it will be lower still. Eventually, so far in the future that the number of years required would stretch the page to infinity, the universe will approach, asymptotically, a temperature indistinguishable from absolute zero. Everything will have radiated away. Everything will have spread out. Everything will have reached the final equilibrium that physics demands. Physicists call this state the heat death of the universe. It is the coldest possible ending to the story. And the cosmic microwave background, the signal Penzias and Wilson found by accident in a New Jersey field while cleaning pigeon droppings out of an antenna, is the current temperature reading of a universe already far advanced along that journey. The discovery made by Penzias and Wilson in 1964 was profound, but it was imprecise. They had detected the radiation and estimated its temperature, but the full power of what the cosmic microwave background contains as a scientific tool required instruments of far greater sensitivity than anything available in the 1960s. The subsequent decades produced an escalating series of missions to measure the CMB with increasing precision, and each one revealed more about the nature of the universe than the last. The Cosmic Background Explorer satellite, known as COBE, launched in November 1989. Its primary mission was to measure the spectrum of the CMB with precision sufficient to determine whether it was truly a blackbody spectrum, the characteristic thermal emission pattern of a perfect radiating body in thermal equilibrium. A true blackbody spectrum would confirm the thermal origin of the radiation, ruling out alternative explanations. COBE's Fierce instrument, the Far Infrared Absolute Spectrophotometer, measured the spectrum with a precision that left no room for doubt. The CMB is the most perfect blackbody spectrum ever measured. The curve of intensity versus frequency matches the theoretical prediction for thermal radiation at 2.725 Kelvin to an accuracy of 1 part in 10,000. No laboratory on Earth has ever produced a more perfect blackbody. The universe, in the thermal fossil of its early fire, produces it effortlessly and at cosmological scale. COBE's second major contribution was the detection of tiny variations in the temperature of the CMB across the sky. The radiation is not perfectly uniform. At a level of about 1 part in 100,000, different regions of the sky show slightly different temperatures. Some patches are a few millionths of a degree warmer than average, and some patches are a few millionths of a degree cooler. These variations, called anisotropies, are the imprint of density fluctuations in the early universe at the moment of recombination. Regions that were slightly denser than average had slightly higher temperatures. Regions that were slightly less dense had slightly lower temperatures. The CMB anisotropy map is a photograph of the universe at age 380,000 years, taken in microwave light, showing the seeds of every structure that has since formed. The CMB anisotropies are the seeds of galaxies. The galaxy you live inside, the Milky Way, the Virgo supercluster it belongs to, the great filaments of galaxies stretching across hundreds of millions of light years, all of these trace their origin to the tiny temperature fluctuations visible in the cosmic microwave background. The map of the cold is also the map of everything that is warm. COBE's team, led by George Smoot and John Mather, received the Nobel Prize in Physics in 2006. The Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001 and operated until 2010, measured the CMB anisotropies with an angular resolution far finer than COBE, producing a map of the temperature variations across the sky with enough detail to constrain the fundamental parameters of cosmology with unprecedented precision. From the WMAP data, scientists could measure the age of the universe, the rate of its expansion,
the fraction of its total energy content that consists of ordinary matter, and dark energy, and the geometry of space itself. The CMB, the thermal remnant of the Big Bang, turned out to be the most powerful cosmological tool ever found.
And then the European Space Agency's Planck satellite, launched in 2009, surpassed WMAP in resolution, sensitivity, and precision. Planck's full-sky maps of the CMB temperature and isotropies are the most detailed pictures of the early universe ever made. They confirm the temperature of the CMB as 2.7255 Kelvin, with an uncertainty of less than 0.001 Kelvin. They confirm the near-perfect uniformity of the radiation, with temperature variations of less than 30 millionths of a degree across the entire sky. And they reveal, in exquisite detail, the acoustic oscillations in the early plasma, the sound waves that were propagating through the universe before recombination, whose imprint in the CMB anisotropy map tells us almost everything we know about the composition and history of the cosmos. 3 missions.
30 years of increasingly precise measurement, and what they found each time was the same number at higher and higher resolution, 2.725 Kelvin. The temperature of the universe, confirmed by instruments of extraordinary sensitivity, consistent across the full sweep of the sky, the same in every direction you look, the same as it was when Penzias and Wilson first detected it in a New Jersey field by accident in 1964. The universe is cold. The measurement is certain. The reason reaches back 13.8 billion years, and what it tells us about our place in the cosmos is worth sitting with for more than a moment. To understand how exceptional warmth is in the universe, you have to understand how the warm regions are distributed across the cold background. Yeah, the picture that emerges from this understanding is one of the most striking facts in all of cosmology. Warmth is not evenly distributed. It is not randomly scattered. It is organized into a structure of breathtaking intricacy, covering a vanishingly small fraction of the total volume of space, separated by abysses of cold that dwarf anything the human mind evolved to comprehend. Begin with stars. The Sun has a surface temperature of approximately 5,778 Kelvin. Its core, where nuclear fusion converts hydrogen to helium, reaches approximately 15 million Kelvin. By the standards of stellar physics, the Sun is an entirely ordinary star, a G-type main sequence star of average mass, average temperature, average luminosity, representing the most common category of stars above a certain mass. Smaller, cooler red dwarf stars, which comprise roughly 3/4 of all stars in the Milky Way, have surface temperatures between 2,500 and 4,000 Kelvin. The most massive, most luminous stars, the rare O-type and B-type giants and supergiants that light up star-forming regions, can have surface temperatures exceeding 50,000 Kelvin. Neutron stars, the collapsed remnants of massive stellar explosions, have surface temperatures shortly after formation of around 1 million Kelvin. These are extraordinary temperatures. Any one of them would instantly destroy any biological molecule. Any one of them represents conditions so extreme that the matter existing at those temperatures is not in any state recognizable from everyday experience. And all of them combined, every star in the Milky Way, every star in every galaxy in the observable universe, and represent a temperature contribution to the universe that is swamped into insignificance by the sheer volume of cold space between them. Here is the architecture. Stars are separated from one another by distances measured in light years. 1 light year is approximately 9.46 trillion kilometers. The nearest star to our own, Proxima Centauri, sits 4.24 light years away. Between the Sun and Proxima Centauri is a volume of space containing essentially nothing. A few atoms per cubic centimeter in the interstellar medium, but no concentrations of matter large enough to retain significant warmth. The temperature of the interstellar medium in the Milky Way varies considerably depending on location, from around 10 to 20 Kelvin in the cold molecular clouds where new stars form, to millions of Kelvin in the hot ionized gas that fills much of the volume between molecular clouds. But these hot regions, despite their extreme temperatures, contain so little matter that they contribute almost no energy to the cosmic budget. Now scale up. The Milky Way galaxy is approximately 100,000 light-years across and contains somewhere between 100 billion and 400 billion stars. If you could shrink the Milky Way until it fit on a page
and then placed the stars on that page proportionally to their actual spacing, they would be invisible. Individual stars are points too small to see at the scale of the galaxy, separated by distances that are vast by any stellar standard, but minute by galactic standards. The Milky Way itself is separated from its nearest large neighbor, the Andromeda Galaxy, by approximately 2.5 million light-years. Between the Milky Way and Andromeda lies the local group Intergalactic Medium, a region of extremely diffuse gas at temperatures ranging from hundreds of thousands to millions of Kelvin, but at densities so low, perhaps 1 atom per cubic meter, that it contains almost no thermal energy. The volume is hot but empty. The product of temperature and density, the actual energy content per unit volume, is negligible compared to what exists inside galaxies. Now scale up again. Galaxies are themselves organized into clusters and superclusters, connected by filaments of matter stretching across hundreds of millions of light-years, surrounding enormous regions called cosmic voids, where almost nothing exists. The cosmic voids, the largest coherent structures in the observable universe, in a span between 100 million and 1 billion light-years in diameter. They contain almost no galaxies, almost no stars, almost no matter of any kind. Their temperature is very close to 2.725 Kelvin. The few atoms that wander into these regions cool to the background temperature and remain there, essentially forever. No stellar radiation is close enough to warm them. The cosmic web, the structure of filaments and nodes and voids that constitutes the large-scale architecture of the observable universe, is mostly cold. The filaments are warm relative to the voids, but cold relative to any star. The cluster centers, where massive elliptical galaxies dominate and hot gas fills the intracluster medium at temperatures of tens of millions of Kelvin, are among the hottest large-scale structures in the universe. And even those enormous regions of extraordinary temperature represent a tiny fraction of the total volume. What fraction exactly? Take the observable universe, 93 billion light-years across, and ask what fraction of its volume is occupied by matter significantly warmer than 2.725 Kelvin. The answer depends on how you define significantly warmer, but by any reasonable standard, the answer is a fraction so small that it challenges any number system designed for human intuitions. Galaxies occupy something like 1/millionth of the volume of the observable universe. Stars within those galaxies occupy an even smaller fraction. The total volume of all stars in the observable universe, were you to somehow compress them all together, would be a sphere smaller than the Milky Way, in a space 93 billion light-years across. The universe is not filled with warmth, punctuated by cold voids. The universe is cold, punctuated by warm anomalies of staggering variety and beauty, but negligible volume. Every planet, every star, every galaxy, every cluster of galaxies, every filament of the cosmic web is, by the numbers, an afterthought. The default is the 2.725 Kelvin of the cosmic microwave background, and almost everything that departs from that default is the exception. In 1990, the Voyager 1 spacecraft was 6 billion kilometers from Earth, on its way out of the solar system, when the astronomer Carl Sagan made a request of the mission team. "Turn the cameras around," he said. "Take one last photograph of the solar system from the outside looking in." The team debated the scientific value of such an image, since most of the planets would be too small to see in any detail, but eventually agreed. On February 14th, 1990, Voyager 1's camera turned back toward the sun. The resulting photograph, a mosaic of 60 images, showed the solar system from a distance no human instrument had ever achieved before. Against the darkness, in a scattered band of light that is an artifact of sunlight diffracting through the camera optics, a pale blue dot is barely visible. It is Earth. Our planet, the only one we know to harbor life, the entire history of human civilization, every person who has ever lived, every thought that has ever been thought, occupies a fragment of a pixel in a photograph taken from the outer reaches of our own solar system. Sagan wrote about that photograph. His words have been quoted many times. But the context these scripts have built around them gives them a meaning that goes beyond their original delivery. He wrote that the photograph underscores our responsibility to one another and to preserve and cherish the pale blue dot, the only home we have ever known. That sentiment is true and important.
But the cold of space adds another layer to it. The pale blue dot is warm. It is extraordinarily, improbably, precisely warm. Not just because the sun is the right size and distance to maintain liquid water on Earth's surface. That part is fortunate but not unique. Many planets orbit many stars at distances that might permit surface liquid water. What makes Earth warm in the cosmic sense is the entire system of coincidences that keeps it from cooling toward 2.725 Kelvin. The magnetic field that deflects solar wind, the atmosphere that traps heat through the greenhouse effect, the oceans that distribute thermal energy across the surface, the moon that stabilizes the axial tilt, the location in the galaxy far from the radiation of the galactic center, the age of the sun that places it in a phase of stable, predictable energy output, the chemical composition of the planet that enables tectonic activity, which regulates the carbon cycle, which regulates the greenhouse effect, which maintains the temperature. Remove any one of these factors. Remove several. The trajectory of Earth's temperature without them leads in one direction, toward 2.725 Kelvin, toward the temperature of the universe, toward the cold that is everywhere, that has always been everywhere, since 380,000 years after the beginning. Now, that will be everywhere long after the last star has gone dark. The warmth is not the baseline. It never was. The cold came first, and the cold will have the last word. But before we arrive at those final implications, we have to understand one more thing about the cold of space. The temperatures we have discussed so far are the temperatures of the universe as it is now, at this point in cosmic history. The cold of space has not always been 2.725 Kelvin, and it will not always be 2.725 Kelvin. The temperature of the CMB is changing, slowly but inevitably, and the direction of that change tells us something about the nature of time itself. The CMB was 3000 Kelvin at recombination 380,000 years after the Big Bang. It is 2.725 Kelvin today, 13.8 billion years later. The ratio of these temperatures, approximately 1,100, is the same as the ratio by which the universe has expanded during this interval. The temperature and the scale of the universe are directly linked. As space expands, the photons of the CMB are stretched to longer wavelengths, and their effective temperature drops in precise proportion. This means the temperature of the CMB is a direct clock for the expansion of the universe. As astronomers trace the history of the expansion, the CMB temperature follows. 1 billion years after the Big Bang, the CMB was approximately 18 Kelvin. 5 billion years after the Big Bang, it was approximately 5 Kelvin. Today, 13.8 billion years after the Big Bang, it is 2.725 Kelvin. In another 13.8 billion years, assuming the expansion continues at a similar rate, it will be around 1.36 Kelvin. The universe is cooling at a rate determined by the rate of cosmic expansion, which is itself determined by the balance between the gravitational attraction of all the matter in the universe and the repulsive effect of dark energy. Current measurements suggest that dark energy dominates this balance, and that the universe will expand forever, the expansion rate remaining roughly constant or even accelerating. Under this scenario, the CMB temperature will continue to drop, approaching absolute zero asymptotically, never reaching it, cooling more and more slowly as the temperature difference between the CMB and absolute zero narrows toward vanishing. The last stars will burn out in approximately 100 trillion years. By that point, the CMB temperature will have dropped to around 0.027 Kelvin. It is still above absolute zero, but 100 times colder than it is today. Without stars to produce new energy, the universe will begin its long descent toward the state called the Big Freeze, or the heat death, in which all available energy has been converted to low-grade radiation uniformly distributed across space. No temperature gradients remain to drive any process, and the universe reaches a state of maximum entropy from which no further change is possible. This is not a scenario for the near future. It is not a scenario for any time frame that human beings have language to express in familiar terms. The numbers involved are so large that they have to be written in scientific notation, and even then, they resist comprehension. 10 to the 100 years. 10 to the 1,000 years.
The universe has existed for a mere 13.8 billion years, which is 10 to the 10 years. The timescales of the heat death are trillions of times longer than the current age of the universe. The cold we are discussing is not just the cold of the present moment. It is the cold of all time, past and future, and most of that time is ahead of us, colder than anything that exists today. But here is the part of this story that the numbers alone do not convey. Here is what makes the temperature of the universe not just a physical curiosity, but a fact with philosophical weight that is genuinely difficult to hold in the mind without something shifting in how you understand your own existence. Think about what it takes to be warm, not warm in the everyday sense of wearing a sweater or standing by a fire, warm in the thermodynamic sense. Well, warm is in maintaining a temperature significantly above 2.725 Kelvin through some active process rather than passively settling toward the background temperature of the universe. What does that require? It requires energy, continuous energy, not a one-time injection of energy, but a sustained flow of energy that can be converted into heat faster than heat is radiated away. And not just any energy. Useful energy in the thermodynamic sense. Energy organized in a way that can be extracted to do work, energy with low entropy. The universe begins with low entropy and moves inexorably toward higher entropy. Every process that produces warmth, every combustion reaction, every nuclear fusion, every chemical reaction in a living cell increases the total entropy of the universe. The warmth is always temporary, and the increase in entropy is always permanent. Stars achieve warmth through nuclear fusion. For a star the size of the Sun, this process lasts approximately 10 billion years. For a red dwarf, it lasts trillions of years. For the most massive stars, it lasts only a few million years before the fuel is exhausted and the star collapses or explodes. In every case, the warmth is a temporary consequence of the consumption of a finite fuel supply. When the fuel is gone, the warmth ends. The object cools. On timescales long enough, it approaches 2.725 Kelvin, and eventually, as the CMB itself cools, it follows the background temperature down toward absolute zero. Planets maintain warmth through a combination of absorbed stellar radiation, internal radioactive decay, and in some cases tidal heating from gravitational interactions with neighboring bodies. Earth's internal heat engine, powered primarily by the decay of radioactive isotopes of uranium, thorium, and potassium, contributes to the geothermal gradient visible in volcanic activity and in the elevated temperatures found in deep mines and ocean floors. But the primary source of warmth on Earth's surface is the Sun, and the Sun is a temporary phenomenon on cosmic timescales. In approximately 5 billion years, the Sun will exhaust its hydrogen fuel and expand into a red giant, potentially engulfing Earth. After that, it will shed its outer layers as a planetary nebula and leave behind a white dwarf, a dense, hot remnant that will cool over hundreds of billions of years toward the temperature of the universe. Yet life achieves warmth through metabolism. The chemistry of life, at the most fundamental level, is a series of controlled oxidation reactions that extract energy from molecular bonds and use that energy to drive the processes of growth, reproduction, and maintenance. A living cell is a tiny engine converting chemical energy into heat and into the ordered structures of biological molecules. The heat is a byproduct and a necessity. Warm-blooded animals, like human beings, maintain a constant body temperature of around 37 degrees Celsius, 310 Kelvin, through a metabolic rate carefully regulated to balance heat production against heat loss. Every calorie of food consumed is ultimately converted into work and heat. Every calorie of heat produced is ultimately radiated into the environment. Life is a temporary, exquisitely organized exception to the thermodynamic tendency of the universe toward cold and disorder. Now ask, given all of this, how common is warmth? In the observable universe, containing approximately 2 trillion galaxies, each containing hundreds of billions of stars, the fraction of volume occupied by objects significantly warmer than the CMB is extraordinarily small. The fraction of those warm objects that harbor the specific conditions necessary for life, as we understand it, is smaller still. The fraction that have actually given rise to life is unknown, but the silence of the cosmos, the subject of Script 2, the 65 years of searching that have returned 0 confirmed extraterrestrial signals, suggests it may be smaller than optimism implies. The warmth required for life is a cascade of improbabilities. Not impossible improbabilities, not miraculous improbabilities, but the kind of improbabilities that, when they are simultaneously satisfied on a single small planet around a single ordinary star in a single galaxy among 2 trillion, should produce a sensation of vertigo in any mind capable of recognizing what has happened. You are warm. You are impossibly, extraordinarily, cosmically warm. The universe is not. Before the full meaning of the cold settles, it is worth acknowledging the extraordinary heat that also exists in the universe, because without understanding the heat, the cold does not have its proper shape. The hottest temperatures in the observable universe today are found in the most violent processes. The jets produced by active galactic nuclei, and the supermassive black holes at the centers of some galaxies that are actively consuming surrounding material. The plasma in these jets can reach temperatures of trillions of Kelvin. The accretion disks around stellar mass black holes where gas spirals inward toward the event horizon reach tens of millions to hundreds of millions of Kelvin. The cores of the most massive stars, during the final stages of nuclear burning before they collapse into neutron stars or black holes, reach tens of billions of Kelvin. And in the brief moments during supernovae, when the collapse of a massive star's core releases more energy in a few seconds than the sun will emit in its entire 10 billion year lifetime, temperatures momentarily reach values that rival the early universe. These are temperatures at which matter is in states that exist nowhere else in the accessible universe. At temperatures above roughly 10 billion Kelvin, atomic nuclei can no longer hold together and dissolve back into free protons and neutrons. Above roughly 10 trillion Kelvin, protons and neutrons themselves dissolve into a quark-gluon plasma, the state of matter that characterized the universe in its earliest moments. These temperatures, while they exist in the universe, exist in vanishingly small volumes for vanishingly small times. A supernova core at 10 billion Kelvin is a sphere perhaps 20 kilometers across, for a duration of fractions of a second. Compared to the 93 billion light-year volume of the observable universe, this is not even a rounding error. The universe as a whole is cold. The hot things in it are staggeringly hot, while the hot things in it are unimaginably rare. And they are all temporary. There is a class of object that deserves special attention in this accounting: white dwarfs. When a sun-like star exhausts its hydrogen fuel and expels its outer layers as a planetary nebula, the core that remains is a white dwarf, a ball of carbon and oxygen roughly the size of Earth, but with a mass comparable to the sun's. White dwarfs are initially very hot, with surface temperatures of tens of thousands of Kelvin, and they have no energy source to replace the heat they radiate away. Over billions of years, they cool. In enough time, a white dwarf will cool completely, becoming a dark, inert object called a black dwarf, radiating nothing, sitting at the temperature of the CMB. Here is the thing. The universe is not old enough for any white dwarf to have yet become a black dwarf. The cooling timescale for a white dwarf to approach the CMB temperature is estimated at longer than the current age of the universe. Every white dwarf that has ever formed is still hot enough to radiate at some level above the background. The universe is simply too young for the first black dwarfs to exist. They are coming. In 100 trillion years, when the last stars have burned out, the white dwarfs they leave behind will continue cooling toward the background temperature. In a quadrillion years, some of the first white dwarfs formed in the early universe will have approached black dwarf status. In far longer timescales, they will have cooled completely. And then the only warm things in the universe will be the slowly evaporating remnants of black holes, radiating their mass away through the quantum process called Hawking radiation, at temperatures so close to absolute zero that even instruments of extraordinary sensitivity would struggle to distinguish them from the background. The trajectory is clear. The direction is unambiguous. The cold is winning, has always been winning, and will continue to win until there is nothing left to contest the outcome. Return for a moment to the moon, not as a destination, but as a physics demonstration. The moon is the most accessible example in our solar system of what happens to a body without an atmosphere and without an internal energy source significant enough to matter, exposed to the same solar radiation that keeps Earth warm. And the comparison between Earth and the moon strips away the variables one by one and shows what the cold of space does when the protection of an atmosphere is removed. The moon orbits at essentially the same distance from the sun as the Earth. It receives approximately the same flux of solar radiation per unit area perpendicular to the sunlight. Yet its surface temperature extremes are dramatically more severe than Earth's, despite the similarity in solar input. This is entirely the result of the moon's lack of atmosphere. On Earth, the atmospheric greenhouse effect alone accounts for roughly 33 degrees Celsius of surface warming compared to what Earth would be without it. Earth's average surface temperature is about 15 degrees Celsius. Without greenhouse gases in the atmosphere, it would be approximately minus 18 degrees Celsius, and the oceans would be largely frozen. But that is the average. The more dramatic role of the atmosphere is in moderating the extremes. The atmosphere absorbs incoming solar radiation, redistributes it through convection and winds, and prevents any surface location from experiencing the full direct exposure to either solar radiation or the cold of space without intermediary. The moon has no such moderation. Every surface location on the moon experiences the direct consequence of its radiation balance, with no atmospheric buffer. The day side, facing the sun, absorbs solar radiation at full strength and reaches temperatures that are limited only by the balance between absorption and emission. With no atmosphere to carry heat away from the surface and no wind to distribute it, the surface rocks can only lose heat through radiation. As their temperature rises until they are radiating energy away, at the same rate they are absorbing it from the sun. At lunar noon, on the equator, that equilibrium is reached at approximately 127 degrees Celsius. The night side of the moon is in shadow. No sunlight reaches it, but the moon still faces the black of space on the night side. What temperature does a surface reach when it is shielded from the sun but exposed to the cold of space? Without an atmosphere to trap the heat of the day or to circulate warmth from the day side, the night side cools through radiation alone. It cools to approximately minus 173 degrees Celsius before some combination of geothermal heat from the moon's interior and radiation from the distant sun prevents further cooling. The night side temperature is limited not by the temperature of space itself, but by the faint thermal emission from the interior and the faint solar radiation scattered from Earth and other surfaces. In a different configuration, in a region far from any star, a surface like the lunar night side would continue cooling all the way to 2.725 Kelvin. The moon's surface temperature swings from plus 127 to minus 173, span 300 degrees Celsius over the course of a lunar month. These swings happen not because the moon is in any particularly extreme location in the solar system, but because it lacks the atmosphere that protects Earth from the extremes its location would otherwise impose. Earth and moon receive the same solar radiation. Earth's surface temperatures range from minus 89 to plus 56. The moon's range from minus 173 to plus 127. Yet the difference is 33 kilograms per square meter of atmosphere, the mass of the air column above every square meter of Earth's surface. That modest amount of gas is the difference between a habitable world and one where the temperature swings by 300 degrees in a month. Space engineers who design missions to the moon must account for all of this. The Apollo lunar module's thermal control system included multi-layer insulation blankets, surface finishes carefully chosen for their reflective properties, and heaters for equipment that would experience the extreme cold of the lunar night. The rovers driven by Apollo astronauts were designed to begin operation from cold soaking at the end of a lunar night, which required their electronic components to be warmed before they would function correctly, and to manage excess heat during the lunar day before the sun had heated the surface to its maximum. The engineering challenge was not a single extreme temperature, it was the range and the speed of the transition. Future crewed missions to the moon and eventual lunar bases will face the same challenge at a larger scale. A building on the moon's surface must be insulated against both extremes. Its thermal management system must handle the transition from -173 to +127 without freezing its inhabitants during the night or cooking them during the day. The solutions being developed for this challenge draw directly on the physics of radiation in a vacuum. There is no other mechanism available. Conduction, in the absence of atmosphere, is only available through direct ground contact with the lunar regolith,
which has very poor thermal conductivity due to its loose, powdery structure. Convection is entirely absent. Radiation is all there is. The moon, in this sense, is a perfect demonstration of the physics that governs all of space. No special conditions are required. No exotic physics applies. The same principles that determine the temperature of a white dwarf, cooling toward black dwarf status. The same principles that determine the temperature of the early universe at recombination. The same principles that set the temperature of the cosmic microwave background apply in their simplest form to a rock sitting in the shadow of a larger rock on the surface of the moon. Temperature in space is determined by radiation. The moon is a perpetual demonstration of this fact, visible from Earth with the naked eye every clear night. The history of human spaceflight is, in one sense, a history of engineering solutions to the problem of the cold. Every mission that has ever left the protection of Earth's atmosphere has had to solve, in its own way, the fundamental challenge of maintaining a habitable or at least functional temperature in an environment where heat management depends entirely on radiation physics. The first satellite capable of measuring temperature in orbit, Sputnik 1, launched by the Soviet Union in October 1957, carried only a simple temperature sensor and a radio transmitter. Within 3 weeks, its batteries had died and the transmitter had gone silent. But before that, it had confirmed that orbital temperature conditions matched theoretical predictions, and the metal sphere reached temperatures ranging from about -60 to +50 degrees Celsius, as it cycled in and out of Earth's shadow every 90 minutes. Every subsequent spacecraft has had to address this problem with increasingly sophisticated solutions. The basic toolkit includes radiation control through surface coatings, which determines how much solar radiation is absorbed and how efficiently heat is radiated to space. Passive thermal control through the design of the spacecraft's geometry and orientation. Active thermal control through heaters, heat pipes, and thermal control systems using fluid loops, and thermal protection systems for entry vehicles that must survive the violent heating of atmospheric entry. The James Webb Space Telescope, as noted earlier, it represents one of the most extreme applications of passive thermal control in the history of spaceflight. Its sunshield is a 5-layer structure of aluminized Kapton film, each layer thinner than a human hair, deployed to an area the size of a tennis court at the L2 Lagrange point, a gravitational balance point 1.5 million kilometers from Earth in the direction away from the Sun. The sunshield reduces the solar radiation reaching the telescope's mirrors and instruments by a factor of 1 million, allowing the observatory to cool passively to -233 degrees Celsius, cold enough to detect the faint infrared emission from the most distant galaxies. The sun-facing side of the sunshield reaches temperatures of about 85 degrees Celsius. The telescope side reaches temperatures below -230 degrees Celsius. These two temperatures coexist on the same spacecraft, separated by 5 layers of thin film and a few meters of vacuum. Webb also carries a cryocooler for its mid-infrared instrument, which must operate at 6 Kelvin, significantly colder than the passive equilibrium temperature of the rest of the observatory. The cryocooler is a mechanical refrigerator that pumps heat from the detector to a radiator facing deep space, achieving temperatures within a few degrees of the CMB temperature. This device, operating in the vacuum of space 1.5 million kilometers from Earth, pushes a scientific instrument to within a fraction of a degree of the temperature of the universe itself, so that the universe's own faint thermal glow does not overwhelm the signals the instrument is trying to detect. The Planck satellite, which measured the cosmic microwave background with unprecedented precision, took this to an even further extreme. Planck's high-frequency instrument operated at 100 millikelvin, 1/10 of a degree above absolute zero, achieved through a multi-stage cooling system that used helium dilution refrigerators to reach temperatures that have no analog anywhere in the natural universe at this scale. A space telescope, orbiting at L2, cooling its detectors to a temperature 60 times colder than the cosmic microwave background,
in order to detect that background with sufficient sensitivity to map its temperature variations to better than 1 part in 1 million. The engineering required to achieve this, the multi-stage cooling chain, the vibration isolation, the thermal management of the entire satellite system. It represents one of the most demanding technical achievements in the history of space technology. And the result, Planck's precise maps of the CMB, is the most detailed portrait ever made of the universe when it was 380,000 years old. There is a certain poetry in this. The universe is cold. The CMB is the coldest natural radiation field in the universe. And to see it clearly, human beings built a machine and cooled part of it to temperatures colder than the universe itself, so that the machine's own thermal noise would not drown out the signal they were trying to measure. The cold is studied by going colder. The baseline of the universe is examined from below. The cosmic voids are the places where the cold is most complete, not the places where space is most empty. And because the voids still contain some gas and the occasional isolated galaxy or galaxy group, but the places where the departure from 2.725 Kelvin is smallest, where the universe most closely resembles its default state, where the architecture of the cosmos built from the tiny temperature fluctuations in the CMB is most clearly expressed as absence rather than presence. The largest known void in the observable universe is the KBC void, named for the astronomers Keenan, Barger, and Cowie who described it in 2013. It extends approximately 2 billion light-years in diameter, an almost incomprehensible scale. Within the KBC void, galaxy densities are roughly 20% below the cosmic average. It is not empty. It contains galaxies, including the Milky Way, which appears to sit near its interior. But it is dramatically underdense compared to the filaments and clusters that define the cosmic web. The temperature within the KBC void is very close to the CMB temperature everywhere. The Boötes void, discovered in 1981, is smaller but perhaps the most dramatic example of a cosmic void currently known. It spans approximately 330 million light-years in diameter. Within its boundaries, only about 60 galaxies are known to exist. A region of space more than 300 million light-years across, containing 60 galaxies, when the cosmic average density would predict thousands. One of the astronomers who first mapped it, Robert Kirshner, reportedly said that if the Milky Way had been located in the Boötes void, we would not have known about other galaxies until the 1960s. But because the nearest galaxy would have been so far away that it would have required modern telescopes to detect. Stand, in imagination, inside the Boötes void. The nearest galaxy in any direction is many tens of millions of light-years away. The night sky, if you were somehow there, would be nearly black. Not utterly black. The CMB is still present, and a few distant galaxies are visible at enormous distances, but the familiar spectacle of a sky populated with visible galaxies and stars would be largely absent. The sky would be a near-perfect demonstration of the actual default state of the universe. Dark, cold, empty. The temperature of that sky, coming from every direction, arriving at whatever object happens to be located inside the Boötes void, is 2.725 Kelvin. There are no nearby stars to provide solar heating. There are no nearby galaxies to provide the diffuse radiation of millions of stars. There is only the ancient light of the cosmic microwave background, and the few photons arriving from galaxies so distant that their radiation contributes negligible heating. An object in the center of the Boötes void, in the absence of any internal energy source, would cool to essentially 2.725 Kelvin, and remain there indefinitely. The voids are where the universe most clearly reveals what it is. The filaments and clusters are where matter has accumulated, where the density fluctuations of the early universe have been amplified over billions of years by gravity into the structures we observe. The voids are where matter has not accumulated, and where the expansion of space has been most effective in stretching the original density fluctuations into below-average regions. The voids are the spaces between the sentences of the universe's story. They are what the universe would be if matter had not had the opportunity to concentrate anywhere. And they are most of the universe. By volume, the cosmic voids constitute approximately 70 to 80% of the total volume of the observable universe.
The filaments, walls, and clusters that contain most of the matter occupy the remaining 20 to 30%. But even within the filaments and clusters, most of the volume is between galaxies, not within them. And even within galaxies, most of the volume is between stars, not within them. And even within planetary systems, most of the volume is between planets, not within them. And even within planets, most of the volume is between atoms, not within them. And even within atoms, most of the volume is between the nucleus and the electrons, not within either of them. The universe at every scale is mostly empty. And emptiness, in the thermodynamic sense, means cold. The cold is not just an ambient condition of space at the cosmic scale. It is the dominant character of the universe at every scale, from the quantum to the galactic. Absolute zero is 0 Kelvin, minus 273.15 Celsius. It has never been achieved. Quantum mechanics forbids its achievement. Even in the most perfect vacuum, even in the most isolated system, the quantum zero-point energy of particles ensures that they cannot be entirely still, cannot be entirely without motion, cannot reach a state of complete thermal arrest. Absolute zero is a mathematical limit, a theoretical floor that nature approaches asymptotically but never reaches. But what would it mean if something could reach absolute zero? At absolute zero, all molecular motion ceases. All quantum zero-point energy is at its minimum. No energy is available to drive any chemical reaction, any biological process, any physical transition. Matter at absolute zero is, in a certain sense, the most perfectly crystallized, most perfectly ordered state that matter can occupy. Every atom is in its lowest possible energy state. The entropy of a perfect crystal at absolute zero is, by the third law of thermodynamics, exactly zero. There is no disorder left to remove. No heat can flow out of it because there is no heat to flow. And crucially, no work can be extracted from it because work requires a temperature difference, and an object at absolute zero has the minimum possible temperature. An object at absolute zero is not just cold, it is thermodynamically inert. It participates in nothing. It contributes nothing to any process that might be going on around it. It is not quite dead, because that implies that something living preceded it. It is simply still in the most absolute sense of that word. The universe will never reach absolute zero while the cosmic microwave background exists. As long as space is expanding and the CMB is present, the minimum temperature any isolated object can reach is the current CMB temperature, because the CMB photons are always arriving from every direction and always being absorbed, always providing some small amount of energy. An object cannot cool below its radiation environment. An object in a radiation field must eventually reach equilibrium with that field. In the current universe, that equilibrium is 2.725 Kelvin. In the far future, as the universe expands and the CMB temperature drops toward absolute zero, the equilibrium temperature drops with it. In a trillion years, the CMB temperature will be so close to absolute zero that the distinction will be essentially unmeasurable, but it will never be exactly zero. The expansion of space carries on, and the expansion is what cools the CMB, and the expansion is driven by dark energy, which shows no sign of diminishing. The universe approaches absolute zero the way a mathematical series approaches its limit, getting closer and closer, never arriving. This is perhaps the most important physical fact about the cold of space. It is not that the cold is absolute, it is that the cold is a direction in which everything is moving, at every scale, at every moment, across all of time, from the 3000 Kelvin of recombination to the 2.725 Kelvin of today, to the fractions of a Kelvin of the far future. The arrow points in one direction. The universe cools. Everything participates in that cooling. Everything that is warm is temporary. Everything that approaches the background temperature is permanent. The cold is not the ending. The cold is the destination. There is a moment in the understanding of cosmic cold where the numbers stop being numbers and start being something else. Not facts, exactly, not data, not facts. Something more like the sensation of having looked over the edge of something very large and very dark, and recognize that what you are seeing is real.
The observable universe is 93 billion light-years across. 1 light-year is approximately 9.46 trillion kilometers, or about 5.88 trillion miles. Multiply that by 93 billion, and you have a distance that reduces any number you have ever encountered in ordinary life to a rounding error so small that it cannot be expressed as a meaningful fraction. The observable universe does not fit in any analogy that uses everyday objects. Solar systems fit. Galaxy clusters sort of fit if you allow yourself to lose track of the actual scale. But 93 billion light-years does not fit. It requires you to accept that you cannot visualize it, can only compute with it, and that the computing is itself a form of trust rather than understanding. Inside that 93 billion light-year sphere, at a temperature of 2.725 Kelvin, there are 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. The stars collectively occupy a volume so small compared to the total volume of the observable universe that the fraction, calculated precisely, is a number with dozens of zeros after the decimal point before the first significant digit. The universe is mostly not stars. It is mostly not matter. It is mostly radiation and dark energy and quantum vacuum fluctuations and the expanding space that carries them. And its temperature is 2.725 Kelvin. Put differently, the average temperature of the observable universe is 2.725 Kelvin. Hey, and that average is dominated overwhelmingly by the vast cold regions, rather than by the tiny warm regions. If you picked a random point in the observable universe, the probability that you would land within 1 light-year of a star is extraordinarily small. The probability that you would land in a galaxy at all is less than 1 in a million. The probability that you would land on a planet in a habitable zone is smaller still by many further orders of magnitude. And the probability that you would land on a planet with liquid water in an active biosphere, the probability of landing in a place with a temperature as comfortable as the room you are currently sitting in, is essentially 0. The warmth is real, but it is surrounded in every direction by cold that extends to distances that make the warmth invisible at cosmic scales. Carl Sagan wrote that if you want to make an apple pie from scratch, you must first invent the universe. The point is that every atom in an apple pie was forged in a stellar furnace, scattered by a supernova, incorporated into a planetary body, processed by geology and biology and agriculture and cooking. The apple pie is a distillation of 13.8 billion years of cosmic history. But there is a thermal version of this observation. If you want to feel warm, you must first create an entire universe, allow it to cool for 13.8 billion years, and allow stars to form, and galaxies to assemble, and supernovae to scatter heavy elements and planets to form, and life to arise and evolve for billions of years, and develop the metabolism that maintains a body temperature, 34 degrees above the CMB, in a room heated to 24 degrees above the CMB, on a planet maintained at a mean surface temperature of 105 degrees above the CMB, by an atmosphere that would not exist without the precise chemical composition of a planet, that would not exist without the right supernova, that would not exist without the right stellar generation, that would not have formed without the density fluctuations in the CMB at the right amplitude. The warmth you feel right now is the product of 13.8 billion years of cosmic history. And again, the cold against which it exists is the default state of a universe that is 93 billion light-years across and mostly empty. Within the solar system, the coldest naturally occurring surfaces are found in permanently shadowed craters near the poles of the Moon and Mercury, regions where the sun's light has never reached in billions of years, where temperatures can drop to as low as minus 238 degrees Celsius, 35 Kelvin. These are almost certainly the coldest naturally occurring surfaces anywhere in the solar system. The outer planets' moons reach similar temperatures. Pluto, visited by NASA's New Horizons spacecraft in 2015, has a surface temperature of approximately minus 230 degrees Celsius, 43 Kelvin. Moving beyond the solar system, the coldest molecular clouds in the Milky Way as the dense clouds of gas and dust where new stars are in the early stages of formation have temperatures of 10 to 20 Kelvin. The Boomerang Nebula, a pre-planetary nebula located about 5,000 light-years from Earth in the constellation Centaurus, currently holds the distinction of being the coldest naturally occurring object in the observable universe that has been precisely measured. Its temperature is approximately 1 Kelvin, below the CMB temperature of 2.725 Kelvin. Wait, colder than the CMB? How is that possible if the CMB is supposed to be the floor? The Boomerang Nebula achieves its extraordinary temperature through a process called adiabatic cooling, the same process that makes a can of compressed gas feel cold when you release the pressure. The nebula is a star in the late stages of its life, ejecting material at an extraordinary rate. Gas is being expelled from the central star at approximately 164 kilometers per second, much faster than the typical stellar wind. As this gas expands outward at high speed, it cools adiabatically, just as gas cools when it expands out of a pressurized container. The expansion is fast enough that the gas cools below the CMB temperature, which means it is actually absorbing energy from the CMB radiation field rather than radiating to it. The Boomerang Nebula is, at present, colder than the background of the universe. This condition is temporary. The expansion will slow, the central star will stabilize its mass loss, and the nebula will eventually warm back up to equilibrium with the CMB as the adiabatic cooling effect fades. The Boomerang Nebula's sub-CMB temperature is a transient phase and a cosmic accident of timing, the result of catching a particular stellar process at a particular moment. In a few 100,000 years it will look different, and its temperature will have risen to match the background. But for now, it is the coldest natural object in the observable universe. A cloud of gas 5,000 light-years away, briefly colder than the ancient light of the Big Bang that fills all of space, achieved by the simple physics of a gas expanding fast enough to cool below its radiation environment. The universe contains exceptions to almost every rule. The floor is 2.725 Kelvin on average, but physics always finds a way. The Boomerang Nebula is also a reminder that the cold of space is not entirely static. Things move, things expand, things cool below and then warm back to equilibrium. Yet the cosmic microwave background is the long-term average, the ultimate reference temperature, the quantity toward which everything tends over long timescales. But the short-term dynamics of individual objects can produce temperatures anywhere on the scale, hot or cold, above or below the average. What cannot happen over timescales long enough for the physics to equilibrate is for an object to remain warmer than its radiation environment indefinitely, without a sustained energy source. And it cannot remain colder than the CMB indefinitely, without something driving the adiabatic cooling. Eventually, everything reaches the background. Heat flows from hot to cold. This is the second law of thermodynamics, perhaps the most fundamental and far-reaching law in all of physics. Yet it is the reason ice melts in a warm drink and not the other way around. It is the reason the smoke from a fire disperses into the air and does not spontaneously reconcentrate. It is the reason a shattered glass stays shattered and does not reassemble itself. The universe moves in a particular direction in time, and the direction is defined by the flow of heat, from warm to cold, from order to disorder, from low entropy to high entropy. The cold of space is the destination of this flow. Not the endpoint in the sense of something that the universe is rushing toward on any human timescale, but the endpoint in the sense of the thermodynamic attractor, the state toward which all processes tend, the minimum energy configuration that the universe, given enough time, will approach. That the CMB temperature today is the result of 13.8 billion years of cooling. The further cooling is the result of ongoing expansion. The ultimate state of near absolute zero is the result of the same process carried on for time frames that defy expression. This connection between the cold of space and the direction of time is not merely metaphorical. In physics, there is a direct relationship between the thermal asymmetry of the universe, the fact that it began hot and is cooling, and the arrow of time that we experience. The reason the past is different from the future, the reason we remember what happened yesterday but not what will happen tomorrow, is connected to the thermodynamic direction of time. The universe began in a state of low entropy. It is moving toward higher entropy, and we remember the past because it is the direction of lower entropy, the direction from which the causal chains of our memories originate. The future is the direction of higher entropy, the direction toward which the universe is heading. The cold of space is, in this sense, not just a physical property. It is a temporal marker. The current temperature of the CMB tells you where in the cooling history of the universe we are. A universe at 3000 Kelvin is 380,000 years old. A universe at 2.725 Kelvin is 13.8 billion years old. A universe at 0.0027 Kelvin is roughly a trillion years old. The temperature is a clock, and it is cooling. The direction of that cooling, from hot Big Bang to cold heat death, is the same direction as the arrow of time. The universe began in an unlikely, low-entropy, high-temperature state, and it is moving toward a likely, high-entropy, low-temperature state. We exist in the middle of this journey, at a moment when the universe is cool enough for chemistry and biology to be possible, but not yet so cold that everything has settled into the featureless equilibrium of maximum entropy. We exist in the window. The window is narrow in cosmic terms. The conditions that permit chemistry, biology, and the maintenance of organized complexity are not available for the full 100 trillion or trillion years of the universe's existence. They are available roughly for the period when stars are actively burning, from the formation of the first stars, a few 100 million years after the Big Bang, to the death of the last red dwarfs, something like 100 trillion years from now. Yet that is a span of approximately 100 trillion years, in a universe that will continue to exist in some form for incomparably longer. Within the full duration of the universe's existence, the era when life as we understand it is possible is brief. We are in that brief era, but only just. The warmth we depend on is itself a transitional state. There is a moment in every discussion of cosmic scales where a fact crosses from interesting to quietly terrifying, and the moment is different for different minds. For some people, it is the scale of the universe, 93 billion light-years, that produces the vertigo. For others, it is the time, 13.8 billion years. For others, it is the number of stars, 10 to the power of 24. For others, it is the silence, 65 years of searching and 0 confirmed signals. For this subject, for the cold of space, yet the moment arrives when you put together two facts that are each unremarkable in isolation and recognize what they imply in combination. Fact 1. The average temperature of the observable universe is 2.725 Kelvin. This temperature is the default state of the cosmos. What things are in the absence of any active energy source. It is what space is, by default, and what everything in it tends toward over time. Fact 2. The temperature required for the biochemistry of life as we know it ranges from approximately 0 degrees Celsius, 273 Kelvin, at the cold limit for most life, to approximately 122 degrees Celsius, 395 Kelvin, for the most heat-tolerant organisms known. The center of that range, the temperature at which most familiar life operates, is around 20 to 40 degrees Celsius, 293 to 313 Kelvin. The ratio between the temperature of life and the temperature of the universe is approximately 300 to 1000 to 2.725. Life exists at temperatures 100 to 400 times higher than the default temperature of the universe. It maintains those temperatures through a continuous process of energy conversion, through metabolism, through the burning of food, through the absorption of stellar radiation, through the greenhouse effect of an atmosphere, through all the mechanisms that conspire to make a planet in a stellar habitable zone behave differently from the cold void that surrounds it. Every second of every day, every living thing on Earth is spending energy to remain 100 to 400 times warmer than the universe. The universe is always trying to equalize the temperature, always sending heat away from warm objects through radiation. And the living things are always converting chemical energy into heat to replace what is lost. Life is a continuous act of defiance against the thermodynamic default of the cosmos. And the terrifying part is not that this defiance is difficult. It is not even that it is temporary. The terrifying part is how narrow the conditions for defiance are. Not every planet can run the metabolism of life. Not every planet can maintain surface temperatures 100 to 400 times above the CMB. The conditions for this particular kind of warmth, the kind that supports chemistry complex enough to build and sustain biological structures, are extraordinarily specific. The right distance from a star, the right kind of star, the right atmospheric composition, the right planetary mass, the right internal energy source, the right magnetic field, the right amount of water, the right geological cycle to regulate atmospheric carbon, the right timing in the star's evolution. Each of these conditions can be stated. Each one, stated individually, sounds plausible, even common. But they must all be simultaneously satisfied. And the probability of simultaneous satisfaction, multiplied across all the conditions, is something that scientists actively debate, and that the 65-year silence of SETI suggests may be very small indeed. The cold is the default, the warmth is the exception, and the warmth that permits life is the rarest exception of all. When Arno Penzias and Robert Wilson detected the cosmic microwave background in 1964, they did not know immediately what they had found. When Robert Dickey's team at Princeton received the phone call and understood, they also understood something that had not been explicit in the theoretical literature but was now unavoidable. The universe has a temperature. The universe has an age. The universe has a history. And the history is a history of cooling. This changes things. Not the physics, which proceeds regardless of human understanding, but the relationship between the human mind and the cosmos. Before the CMB was discovered, the universe could be imagined as eternal and static, or as infinitely varied, or as a stage without a play, a space without a temporal direction. After the CMB, those imaginations became untenable. The universe has a direction. It is cooling. The temperature of the radiation field that permeates all of space is a thermometer measuring how long the cooling has been going on. And the reading on that thermometer, 2.725 Kelvin, places us at a specific moment in cosmic history, neither early nor late by cosmic standards, at roughly the midpoint of the era when stars are possible, at a time when the universe has cooled enough to be transparent, but not so cold that complex chemistry is impossible. We are here at this specific temperature, in this specific moment, not by coincidence, in the trivial sense. The universe did not plan it, but the conditions of this moment are what permit us to be here at all, and recognizing that changes the quality of the cold. The cold is not our enemy. The cold is the context. The cold is what makes the warmth unusual enough to be remarkable, precious enough to be worth protecting, unusual enough to be, in the most literal physical sense, extraordinary. George Smoot. And one of the scientists who discovered the CMB anisotropies with Kobe in 1992 described seeing the first maps as like looking at the face of God. That description carries whatever philosophical weight you choose to give it, but the physical reality behind it is objective and precise. Those ripples in the CMB temperature, those variations of a few millionths of a degree across the ancient microwave sky, are the seeds of every structure in the universe, every galaxy, including the Milky Way, every star, including the Sun, every planet, including Earth, every living thing that has ever existed. All of it traces its origin to those tiny temperature fluctuations in a radiation field that now fills all of space at 2.725 Kelvin. The cold of space is not just the absence of warmth. Yes, it is the record of the process that created the conditions for warmth to exist at all. Without the precise spectrum of the CMB, without the specific amplitudes of its anisotropies, the density fluctuations that grew into the cosmic web would have been different. The galaxies that formed would have been different. The stars that ignited would have been different. The planets that assembled would have been different. The chemistry that gave rise to life would have been different if it arose at all. The cold is part of the story of warmth. The story of how 2.725 Kelvin gave rise to 310 Kelvin is the story of 13.8 billion years of cosmic history. It is the longest story, and it ends at this moment, at this temperature, with a species capable of measuring the cold and asking what it means. Remove the sun from the solar system. Remove it entirely in the imagination and ask what happens to Earth's temperature over time. Immediately, the surface temperature begins to fall. The oceans, which contain an enormous thermal mass, warm the atmosphere for decades through evaporation and thermal radiation. The clouds that form from the evaporating ocean reflect some of the surface's thermal radiation back down, slowing the cooling. But the clouds themselves freeze and fall as ice and snow. The ocean surface freezes. The freezing surface reflects more of Earth's own thermal emission back into space, accelerating the cooling. Within a century, the surface temperature has dropped to around minus 70 degrees Celsius in most locations, but not to 2.725 Kelvin. Not immediately, not for a very long time. Earth's interior is hot, heated by the radioactive decay of unstable isotopes. This internal heat leaks through the crust at a rate of about 47 terawatts, distributed across the entire surface of the planet. Without the sun, this geothermal heat would be the only energy source keeping the surface above absolute zero. Subsurface liquid water would persist for a very long time, kept liquid by geothermal heat. Chemosynthetic life, life that draws its energy from chemical reactions rather than sunlight, could survive for billions of years in the deep ocean, or in the warm, chemically rich vents where geothermal heat is concentrated. Eventually, over billions of years, the radioactive isotopes would decay to stable elements, and the geothermal heat flux would diminish. The deep ocean would eventually freeze. The atmosphere would collapse, as condensing first as liquid nitrogen and oxygen, then as solid ice, piling up on the frozen surface as the temperature dropped toward the minimum achievable with the remaining heat sources. The faint thermal emission from stars in the galactic neighborhood, the galaxy's diffuse stellar background, and ultimately, in the far future, the cosmic microwave background alone. Earth without the sun, given enough time, would cool to 2.725 Kelvin. The cold would have the last word. The warmth of an entire planetary history would be radiated away, photon by photon, into the void. And the void would absorb it without any detectable change. This is what the cold is. Not an ending in the dramatic sense. Not a collapse or an explosion or a sudden catastrophe. A cooling, a gradual, irreversible approach to equilibrium with the universe. A settling of temperature toward the background. An old house slowly releasing the heat of the day into the cold night air, until morning. And then there is no morning. There's a question that hovers over all of this, unasked, but impossible to ignore. What does it mean to be alive in a cold universe? Not philosophically, in the sense of seeking meaning. The physics doesn't offer meaning. But phenomenologically, what is the experience of being a warm, organized, conscious system in a universe that is mostly cold, mostly empty, mostly old, and mostly indifferent? The answer your body gives you every moment is, it feels normal. It feels like the default. The warmth of your skin, the warmth of the room, the warmth of food and drink, and the sun on your face, these feel like the baseline from which cold is a departure. But that intuition is precisely backward. The cold is the baseline. The warmth is the departure. Every warm sensation you have ever had has been generated and maintained at enormous thermodynamic cost against a universe that is trying, gently and persistently, to equalize the temperature. The feeling of cold, the genuine cold of a winter night, or an ice bath or a cold swimming pool, is closer to the universe's truth than the warmth you take as normal. And the genuine cold of space, the 2.725 Kelvin of the cosmic microwave background, is so far beyond anything your nervous system was designed to register that it might as well not be on the same scale. Human beings have no sensation for 2.725 Kelvin. We have no way to feel it. We experience cold as the loss of heat from our bodies, and our bodies cannot cool to 2.725 Kelvin and survive.
Yet we can know the temperature of the universe intellectually, can measure it with instruments, can compute its implications, can trace it back to the Big Bang and forward to the heat death. But we cannot feel it. We are too warm to feel it. Our warmth, the same warmth that makes us capable of having a nervous system, capable of measuring, capable of asking what this means, prevents direct contact with the universe's actual temperature. This is not a limitation to be overcome. It is a fundamental feature of the situation. The warm observer and the cold universe are not in equilibrium. That is exactly the point. The observer exists because the equilibrium has not yet been reached. The day the equilibrium is reached, the observer is gone. Diana Scognamiglio, the researcher at NASA's Jet Propulsion Laboratory who worked on the Cosmos Web dark matter map, was described as experiencing a moment of recognition when she compared her new map to the older ones. The room went quiet, and then people started clapping. Scientists recognizing something they had not expected to be achievable yet. The measurement of the CMB temperature, done with sufficient precision to see its tiny variations, produces a different kind of recognition. Quieter. Longer lasting. The recognition that the ancient, cold, nearly uniform radiation that fills all of space is the oldest information accessible to any instrument humanity has ever built. That the 2.725 Kelvin we measure today is a continuous thread from 13.8 billion years ago. That the photons arriving in our instruments right now, right here, left their source when the universe was 380,000 years old, before any star existed, before any heavy element had been forged, before any planet had assembled, before any chemistry complex enough to build a cell had the raw materials to begin. That the cold has been traveling toward us for the entire history of everything. Enough time passes, not enough for you to experience, not enough for human civilization to endure through, but enough in the language of physics, of cosmological timescales, of the kind of time that the cosmic microwave background has already traversed. The last star burns out, not dramatically, not explosively. It is a red dwarf, the smallest and most frugal of stars, dimming gradually over hundreds of billions of years as its hydrogen is consumed. When the last of it is gone, the star simply dims, the surface cools, and the luminosity falls toward zero. The object is now a black dwarf, or will be, in the further billions of years it takes to cool toward the background temperature. The universe is dark. Not completely. The cosmic microwave background still fills all of space. Dark matter halos still occupy the same volumes they have always occupied, shaped by the same gravitational dynamics. White dwarfs, former stellar remnants, are slowly cooling, emitting faint thermal radiation that becomes less detectable with every passing epoch. Neutron stars, the ultra-dense remnants of massive stellar explosions, are cooling. Black holes, the most extreme objects in nature, are slowly evaporating through Hawking radiation, emitting photons at temperatures inversely proportional to their mass. At a black hole the mass of the Sun would take approximately 10 to the 67th years to evaporate completely. A supermassive black hole at the center of a galaxy would take 10 to the 100th years, or more. These timescales are so large that the current age of the universe, 13.8 billion years, is not a rounding error. It is less than 1 part in 10 to the 91st of the evaporation time. During all of this time, the CMB temperature continues to fall. It is falling now. It fell yesterday. It will fall tomorrow. Slowly. By fractions of a Kelvin over billions of years. But always falling. Always cooling. The universe as a whole heading, step by step, toward the condition that physics calls the heat death or the big freeze. The state of maximum entropy in which no temperature gradients remain. No work can be extracted. No process can proceed. And the universe exists in a static, featureless equilibrium at a temperature indistinguishable from absolute zero. This is where the story ends. Not with a bang, not with a dramatic collapse, with a cooling, a settling, a silence so complete that there is no one left to hear it, no instrument sensitive enough to measure it,
No mind left to recognize that the silence has begun. The cold wins. It has always been winning. The warmth we know, the warmth that built this story, the warmth that powers the instrument reading these words, and the mind understanding them, is an exception that the universe made, briefly, improbably, for reasons that physics describes but does not explain. And the description is enough to be astonishing. Hold a grain of sand at arm's length. That tiny patch of sky contains 10,000 galaxies, each typically holding hundreds of billions of stars. Each of those stars is a temporary exception to the cold of space. Each of those galaxies is a temporary island of warmth in an ocean of 2.725 Kelvin that extends in every direction without a break you can point to, without a boundary you can find, without an end that any instrument has detected. The grain of sand covers a patch of sky that is also home to the cosmic microwave background, arriving from every direction simultaneously, ancient and featureless and cold. The galaxies in that patch are warm by the standards of the CMB. Some of their stars are hot. Some of their planets are warm enough for chemistry. Some of those planets, at least one, are warm enough for life. And life, on at least one of them, evolved the capacity to build instruments that can measure the temperature of the universe, trace it back to its origin, and ask what it means. The measuring and the asking are themselves temporary. They are products of the warmth. When the warmth ends, the measuring and the asking end with it. The cold that remains does not know it was ever interrupted. The CMB photons that fill the cold space continue their journey, stretched to longer and longer wavelengths, cooling toward the mathematical limit that is absolute zero, carrying information that there is no longer anything alive to receive. But right now, at this moment, at 13.8 billion years into the universe's history, at 2.725 Kelvin in the void, and 310 Kelvin in the mind reading this sentence, the warmth is still here. The exceptional, improbable, temporary warmth is still here. And the cold that surrounds it is exactly as deep and as vast and as old as it has ever been, as old as the universe itself, as old as the light that Arno Penzias found in a New Jersey field while cleaning pigeon droppings out of an antenna. That light is still traveling. It will be traveling when everything warm has gone cold. It is the oldest signal in the universe, and it says the same thing it has always said to every instrument sensitive enough to hear it, from every direction simultaneously, without pause or variation, in a frequency your body cannot feel, and a temperature your nervous system cannot register. It says, cold, cold and vast and ancient and still. The universe speaks in one voice, and the word is cold. The terrifying truth about how cold space really is turns out to be several truths, stacked on top of each other, each one carrying more weight than the one before. The first truth is that cold in space does not work the way cold on Earth works. There is no medium to conduct heat away from a warm body. There is only radiation, and radiation, without a mirror to reflect it or a medium to absorb it, travels forever. The cold of space is not actively cold in the way a refrigerator is cold. It is passively cold in the way that nothing is cold. The absence of a medium means the absence of conduction, and without conduction, temperature in space is entirely a function of what radiation a body absorbs and emits. The second truth is that the temperature of the universe has a specific measurable value, not a range, not a rough estimate, but a precise number measured to 4 decimal places by instruments of extraordinary sensitivity, 2.725 Kelvin. Yet this is the temperature of the cosmic microwave background, the thermal fossil of the Big Bang, the light that was released when the universe was 380,000 years old, and has been traveling and cooling ever since. It is the minimum temperature anything in the universe can passively cool to. It is the floor. The third truth is that 2.725 Kelvin is extraordinarily cold by any human scale, colder than liquid helium, colder than the interior of any MRI machine, colder than anything your body or your technology or your food has ever encountered outside of a cryogenic laboratory. A temperature that, from the perspective of your nervous system, would be indistinguishable from absolute zero. because you would not be alive to feel the difference. The fourth truth is that this temperature dominates the universe by volume. The warm things, the stars, the planetary surfaces, the galactic disks with their gas and dust and radiation, occupy a fraction of the total volume of the observable universe, so small that a calculation of it produces a number with dozens of zeros after the decimal point. The cold is not a background condition. It is the foreground. It is what the universe is, and the warm regions are the exceptions. The fifth truth is that the cold is getting colder. Not quickly. Not on any time scale that biological or civilizational time has language for. But the direction is unambiguous, the physics is certain, and the endpoint is as close to absolute zero as makes no practical difference on timescales long enough. The universe is cooling. It has always been cooling, and every warm thing in it is a temporary exception to a rule that physics enforces without exception and without mercy. The sixth truth is that your warmth is the most extraordinary anomaly in this cold universe, not the most significant, whatever that might mean in a universe indifferent to significance, not the most valuable, whatever that might mean in a universe without a value system, but anomalous in the precise physical sense, departing dramatically from the average, requiring a cascade of specific conditions to maintain, and sustained at an energy cost that, measured against the background of 2.725 Kelvin extending in all directions without limit, amounts to a defiance so improbable that the word exceptional is a profound understatement. You are warm. The universe is cold. The universe is mostly cold, overwhelmingly cold, and cold in a way that makes warmth exceptional to a degree that reduces the warmth to statistical invisibility at cosmic scales. And yet the warmth is real, and it is here. And it contains, at this moment, everything that can think or feel or ask what this means. There is a moment described by many of the scientists who have worked on the CMB, who have seen the Planck maps and the WMAP data and the COBE spectrum, where the cold stops being an abstract number and becomes something else. Not something comfortable, not something reassuring, but something the size of what it actually is, the temperature of the universe. A physical fact as large and as real as the universe itself, accessible through instruments built by one warm species on one warm planet in one warm corner of one galaxy among 2 trillion. And for the roughly 100,000 years that our species has existed, compared to the 13.8 billion years the cold has been present. The cold was here before us. The cold will be here after us. The cold is here now, separated from the warmth of this moment by the atmosphere above, the magnetic field beyond that, the solar radiation that maintains the surface temperature, the greenhouse gases that trap enough of it to keep liquid water on the surface, the oceans that distribute the warmth evenly enough to support a biosphere, and the biosphere that, over 4 billion years, has maintained all of the conditions necessary to sustain itself. Remove any one of those layers, and the cold is immediately closer. The grain of sand is still at arm's length. The galaxies behind it are still there, and the cold between every one of them. Hey, between every star, between every galaxy, between every cluster, between the Milky Way and Andromeda, and every supercluster and every filament and every node of the cosmic web, extending into every void for hundreds of millions of light years in every direction, deeper than any instrument has yet seen and deeper than any instrument will see for as long as warmth persists, is 2.725 Kelvin. You are here briefly in the warmth. The cold is everywhere, and it is patient. It has all the time in the universe.